So, hello, I'm James St. John, and this is a podcast where we're going to talk about stuff. I'm here today with the podcast co-host.
Champri Singh. Hey, how you guys doing? We're
We're out here, making moves, making money. But yeah, so we just started this podcast because we have a ton of interesting conversations about AI, science, physics, and stuff like that. So we're just gonna start recording and see where the conversation goes.
yeah.
Yeah. So Jimmy, what's something you've been looking up this week?
Yeah, so I'm writing a quantum mechanics paper, so I'm just picking a topic that interests me relating to quantum mechanics. So what really interests me, related to quantum mechanics is the application of quantum mechanics through quantum computing. So, there's a lot of buzz going on about that field nowadays. You'll find it in a lot of science news outlets. But, I feel like now that I'm taking a class on it and I'm looking at the math behind it after taking my, fundamental courses, I feel like I'm sort of, you know, grabbing an intuition about how that works. And I see a lot of potential in it.
What do you mean by grabbing intuition?
Yeah, so once you like an example could be just learning how matrices operations work. And qubits and superposition and whatnot, they operate on that math foundation. Like working with linear algebra and just getting comfortable with it. And I guess once you practice enough, you sort of gain an intuition about how that all works.
Okay.
Yeah.
So, all right, this is something I've always struggled with, and I'm not trying to put you on the spot. Just I have a question. Like, could you actually explain what a qubit is?
Okay. Yeah.
If you can't, that's
Yeah.
fine. We'll come back to it at some other point. But
All
if
right.
you can, because I
All right.
like I've looked up definitions of it before and whatever, but I still don't really know what it is. So.
Okay. Yeah. So from your intro to electrical engineering course that you learn about how a transistor works.
Mm-hmm.
And basically the two modes of operation for a transistor is when it's either on or off.
Mm-hmm.
On being that there's voltage going through it, off being there's no voltage going through
Okay.
it, right? And that's relating to a classical bit, and that's
Right.
that's represented by a 0 or a 1, right?
Mm-hmm.
But those are two definitive states, right?
Yeah.
It's like you're either in a 0 or a 1, right?
Right.
Now, in a sense, you could also call that a qubit, believe it or not. So, what a qubit is that it uses the property of superposition from quantum mechanics, right? Like, you just have your system, and it could be represented by, many terms, right? And your system is sort of in the state where you're in all states at once.
Right.
So, what that means is that you don't have a definitive statement about your system until you actually measure your system, right?
Right.
So your system could be in like superposition or existing in like all these different states before you measure it, and then after you measure it, your system collapses to one of the possibilities there are for your system.
Mm-hmm.
So what that means is that how your classical bit was either a 0 or 1.
Right.
Your quantum mechanics system could be in like both a 0 and a 1. It could be in a superposition, and it won't be either one until you actually measure it, and that's when it'll collapse like a classical bit, a 0 or a 1, right?
So it can, is it only two possible states, or is it four possible states? I don't remember.
So depending on the number of qubits you have, if you just have
just a single qubit.
Yeah, so just a single qubit could have two states.
Okay.
Yeah, it could be a 0 or a 1, but it's actually in a superposition of both those states until you measure it.
So this is where my understanding, like I've heard that before, and that makes sense to me.
Okay.
But how would you be able to do calculations?
Yeah.
With a single qubit, if you can't, if as soon as you measure it, it turns into a classical bit, right? So like, how are you doing calculations before you measure it?
So I'm no expert on this. Let me give this disclaimer, But from what I read, is that it's not the ability of giving you the straightforward answer you want.
Mm-hmm.
It's more so it gives you the ability of calculating random answers. So, like, think about it like this: if you had like a complicated problem you're working with, right?
Mm-hmm.
And you just wanted to see all the different solutions there are to that problem, but you wanted to, like, a classical computer would do that, systematically, and it would just go through a solution one by one, Whereas
Right.
quantum, with your qubits, it's able to calculate all these random solutions all at once, right? Because you're in a superposition of like all these different solutions that you could potentially have to whatever problem you're looking at, right? And you know, it's able to calculate that all at once essentially, and it just gives you a lot more processing power.
Right. That's where I still don't get it.
Yeah. So
it's like how.
So how would you get upon the answer that you want, right?
Well, more so. So, for example, if you plotted a graph on computer code, so say MATLAB, because that's what we're familiar with, it would start plotting at your first x value and stop plotting at your last x value. Like, it would work towards it in that order.
Okay.
From your first x value to your last x value. So you plotted like a straight line from 1 to 10, from x equals 1 to x equals 10. And so you're saying a quantum computer would just plot them all randomly until they were all done?
Well, you could think about it more like
might not be
it would plot randomly until you get like the solution that's similar to the one that you're looking for. Not so that it's not doing a specific task.
Mm-hmm.
So to say it's looking for a specific solution. So
it's normally looking for a specific solution. That's what it would be useful for, you're saying.
Well, it's using probability to come upon like a specific solution that you want.
Okay.
Yeah. So, I mean, you could also go... It gets much deeper than that, Because
Mm-hmm.
you could start using... Because each of the superpositions will have, like, states, right?
Right.
And each of the states will have, like, a different probability to them,
Right.
Like, this is a chance of this occurring, this is a chance of this occurring, And... in a good system, the probability will all equal to 1,
Right.
It's like if you take the probability of each state and then it'll just be, it'll add them all up to 1, right?
Yep.
So, but you can make it so that, each of these states will actually have a phasor term to that. So what that means is that you could represent it by some sort of, complex sinusoidal wave, right?
Mm-hmm.
So, but if you have them like in a superposition, you could have it so that you could have some sort of interference that happens. So there might be terms that you don't, that you can apply like a phasor that it just cancel out another term. So we get like constructive and destructive interference.
So it's like the sum of the solutions thing.
Exactly.
Is a solution.
Yeah. So you're just gonna have like a lot of interference happening and then you're sort of bringing out the solutions that you do like, and then the ones that you don't want, they're just naturally being canceled.
Oh, interesting.
Yeah.
Interesting. All right. Interesting. Yeah, that doesn't really answer my question though. But let's move on though, because...
Alright, wait, what was your question?
I guess my question is more, how do you measure something? How can you do calculations with something without measuring it? Without getting some type of signal from it?
You can.
So then, so you have this qubit that's in... So it's in a superposition of states.
Yeah.
A mixture of states.
Uh-huh.
But why is that useful then, if you can't measure it?
Well, it's not that it's more so useful. It's just the way it is, actually. So, believe it or not, so let's round this back to the double slit experiment, right?
Right.
So, we see light as sort of a particle prior to the experiment,
Right.
And then when we make it go through the double slits, we see this diffraction pattern, right?
Mm-hmm.
And that's explained by justifying that light could be a wave,
Right.
not just a particle, sort of say. And that's how we see the pattern that we see, right?
Mm-hmm.
Okay, but did you know that you could do that experiment with just one photon?
Yes.
A single photon, right?
Yep.
So
Freaky.
yeah, right. But what that means is that when it's going through the double slit, two slits, right? It has to simultaneously exist in both slits. So you can say it's in a superposition of being in one location and the other, but you can't really measure it.
Right.
And that's the answer that quantum mechanics gives you, whether you like it or not.
No, I know.
Yeah.
That I get. So you're saying
Okay.
then when you have a qubit,
You're just assuming that all these states exist in a superposition.
okay.
Yeah, so you don't know that in all those states before you measure it, but you know it will come to one of those states after you measure it.
But the states being only a 1 or a 0.
No, there's actually, if you have more than a single qubit.
Right. Oh,
Yeah.
I see now. Okay.
Yeah, if you have
I
like.
see. Yeah, because there was.
And
Like,
it rises exponentially,
Yeah,
I'm
it's
not,
something.
Yeah.
I think it's 2 to the power of the amount of qubits, or it's the amount of qubits to the power 2. I think it's 2 to the amount of power of qubits, 2 to n.
Yeah, roughly.
And so, we'll give you your actual computing power, whereas a normal computer is like the amount of.
It's exponential. Once you start putting in a lot of
Yeah.
variables, it'll just blow up. It won't. It'll slow down.
Interesting. Okay. So the only time you're actually doing a calculation though is when you actually measure a qubit.
Yes. Exactly.
You just don't know what state it's going to collapse into.
Yeah.
Oh, and then you could make some type of probability distribution based on that, I would imagine. So that's what you mean, like, it wouldn't be exact, it would be like you'd statistically be getting to,
Yeah, so you
first,
apply,
you'd statistically be getting closer and closer to your answer.
So, like, there's this thing where in Shor's algorithm, so Shor's algorithm is, like, dealing with, like, the factorization of a large prime number, right?
Right.
So this is dealing with, encryption,
Mm-hmm.
So, I mean, there's a step in that whole process where you have like a Fourier transform. So you're basically applying weights to all your different, sort of solutions that you could have, right?
Right.
And then, you're sort of just organizing and figuring out, the best solution to your problem, and that's just how it's working,
I don't know.
Yeah.
Yeah, no. I'm.
It's very complicated,
Yeah, I mean, yeah.
Yeah.
I'm personally on the side of. I'm very skeptical about quantum computing, because a lot of people talk about it like we already have it, and I guess like we have it in the sense of like we can make a, 2-qubit system or something like that, but like, I don't know if they get more complicated than that, like in terms of what we actually have and what we can actually use. So, I'm not skeptical that it could exist. I'm skeptical that it's, it already exists in a useful capacity.
I see. So you don't feel like there's more potential? Is that it?
No, I think there is. Like, I don't know if you remember a few years ago, one of the students at Adelphi, I think I graduated with him, Aditya. He did research at Brookhaven National Labs and they have like a quantum computer, but I think it's only like I don't know. I don't want to speak incorrectly about the system that Brookhaven has, so I'll look that up later. But like they have a quantum computer and it only has like it doesn't have a lot of qubits, so they can do the measurements that they can do aren't useful. Like a normal computer could do them faster because they don't have enough qubits. But obviously, once they get more and more, if you add a single qubit more, that exponentially increases the processing power or computing power, and that's not the same with a normal computer. So I'm like skeptical when people talk about quantum computing in terms of like some people are like like quantum computers are gonna be the next big thing, like all that stuff. It's like I think they'll have really niche uses, probably like people talk about how they'll be useful like with code breaking and like encryption breaking and stuff like that, and like for mining Bitcoin and whatnot. I'm just I don't think it's gonna change. well, that's getting off topic, but I don't think it's going to change like day-to-day activities. It will just change like some fundamental things about computers, but it's not going to like make my YouTube video load faster. You know.
Well, who knows? Like all the systems that we know of, they operate on classical computers. You know. So
Right.
once we could like figure out, the possibility of quantum computing, once we like figured out how to actually make the computer, because right now the qubits that we have are not much, as you said.
Right. Right.
Like once we have like more qubits and everything,
And that's another thing. Like I'm gonna look into why is it difficult to get multiple qubits? Like I'm sure it's difficult to get a single qubit. Like I just don't know why.
Yeah. So I mean, I saw this lecture by somebody. I don't remember her name.
Wow.
She was talking about how the more qubits you have, the more susceptible it is to
Susceptible?
Yeah, susceptible, whatever that word is, to catch error. It's like as you increase the amount of qubits that you have, you're increasing the volume that you have. You
Right.
know, but you're also making it more vulnerable to error.
Really?
Yeah, for reasons I'm not aware.
You're not
of.
sure, yeah, but interesting.
But she said that there's more error when you have more qubits. So obviously there's a lot more.
So I guess there's there's like a sweet spot of amount of qubits.
Well, it's
like you want it enough that it could do a calculation fast.
Well, it's just that our processes of just handling qubits are probably not at where they should be right now.
Oh, so it's like a
we just need better.
A computer, like we can't build them like build a quantum computer with enough qubits that's like accurate enough, or something like that. So it's like it's like a physical error that we're
exactly
running into.
Yeah.
Okay.
So we just need better instruments and equipment. I'm
But
assuming.
I wonder though, because generally when we talk about a qubit, we talk about a single electron, right?
Okay.
You're talking about like which way it's spinning, and that's like if it's spinning one way, if it has positive 1/2 spin, it's like a 1, and if it has negative 1/2 spin, it's like a 0, right?
Okay.
So I wonder if there's an error. There's like an actual limitation with the amount of of certainty, like with like that you can make that measurement. So because if you're measuring single electrons, I mean that's like got to be fundamentally difficult to do. Not just like because it's not like it's difficult to do because the signal's so small. It might just be difficult to do because like the only way to measure it is like with another electron. Or with a photon, and then you're changing the measurement somehow. So I don't know. I'm making shit up.
I mean, when we have more than one qubit, right? You could say that we have more than one electron, and you have to worry about electron interaction. With
like,
the Coulomb force.
Oh god,
Yeah,
that's
so,
like electrodynamics.
Yeah, exactly.
That's quantum electrodynamics.
Yeah, so if you're gonna have more qubits, you need to take into account for all those factors.
That makes sense. That's actually really interesting then, because that sounds almost like the hydrogen atom, how you can solve for the energy levels of it perfectly, in quantum. But then as soon as you add another electron, right, and another proton, you can't solve for helium perfectly because the electrons interact in such a complicated way.
Exactly, right? So, I mean,
Interesting.
quantum computing is still it hasn't even like taken a step farther than a finish line. From the starting point.
It got to the finish line already?
No, right? Like we still don't even have like a fully fledged quantum computer to even make sort of assumptions
right.
of what it can or cannot do.
Exactly. Yeah, that's what I was kind of talking about. Yeah.
But from what I see, its potential. I feel like it would definitely change a lot of things, because a lot of the stuff that we do nowadays, like what we use in our electronics, operate on the classical system,
Mm-hmm.
But,
right.
Who knows what a quantum computer could allow us to do, like, if we're allowed to, just process faster,
Mm-hmm.
like, we could probably take a lot more data effectively, like better sensors,
Oh, like crunch raw data?
Yeah.
Better? Yeah.
Honestly, like, whatever, we could get more discrete data, from like to the smallest bits that we have, we could record that.
I see. Yeah.
Capture it.
So it's like get like the best resolution of data you possibly can.
Yeah.
because now that's no longer
Mhm.
a bad thing.
Yeah.
The
So
voluntary
I
way.
mean, this is a very long stretch, but if we're able to do that, who knows? Maybe we'll be able to study. I mean, this is already a thing that researchers have said. Like we could study chemistry at a better level. We can make molecular simulations better by actually simulating them on the atomic scale.
Yeah, that I can understand why you would need a quantum computer for. I mean, just like the sheer difficulty. Oh, that actually makes sense though, right? Because if you're trying to like simulate how a molecule forms, this is what like a lot of atomic physics is. Like how atoms interact and whatnot, and so if you were trying to simulate how two atoms would form a molecule, there's probably some quantum mechanics that goes on there.
Definitely.
So what, right? Because I guess more so quantum mechanics is generally more interested in like how neutrons and protons form a nucleus of an atom, but like even so, like the strong and the weak force and whatnot. So it's like if you're actually using quantum mechanics to simulate quantum mechanics, right? Like
it sounds very obvious,
It's weird. It's like obvious, but like not obvious. I don't know.
It's
that's something I never thought of.
It's just that we've been working so long on the macro scale. We
got
really,
so far.
Yeah, we didn't think we could get
Didn't even matter.
onto the quantum scale. And then but these are the type of questions we're asking. Like how can we look at systems at the quantum scale?
Mm-hmm.
So we're gonna need quantum scale. Sort of measurement.
That's actually something. A lot of people, because a lot of people are still like, I shouldn't say a lot of people, but I know that there's still a school of thought that people say, well, quantum mechanics is just kind of like the next trend in the way that we look at the physical world. Like, because before quantum, the previous best thing before quantum was general relativity, which is still extremely accurate, right? It's just not good at describing small things. It's beautiful at describing big things. And so, relative to us, And then, but the the thing before general relativity was Newtonian mechanics and stuff, and there's obviously problems with that in certain cases and stuff. So I think some people even think like quantum is just like it's not the final form, if you will, of the evolution of physics. Like somebody will
definitely
come along and solve some crazy equation or find the magnetic monopole or something like crazy.
I mean,
cold fusion. I don't know.
Yeah. So, when we look at even quantum mechanics itself, you can actually say points out that it's not complete when we look at entanglement.
Yeah.
So entanglement occurs, but we don't know why it occurs. And Bell, the one who formed the Bell inequalities, he said that quantum mechanics might just be incomplete or just wrong.
Yeah.
Because we can't understand definitively what's happening when we look at entanglement. So I mean, I definitely feel like there's more to be done. Especially explaining why entanglement happens. We just need to figure
out. We
should
have a special guest, a quantum professor, on this podcast.
Yeah, like what are the ways they're trying to figure out how entanglement works?
Yeah.
What sort of experiments they're doing?
I do know.
You do.
I do.
Okay, so like what sort of direction are they taking?
Oh no! I know what you're talking about. I don't know. I don't know anything about that.
Okay.
Yeah. All right. So yeah, that's interesting. All right, we'll wrap it up. We'll be back soon, solving more of the world's problems. Next we're gonna tackle politics. I'm kidding. But yeah, so we'll come back with another interesting physics or something topic. Something that we're interested in. Maybe we'll try and get a guest.
Okay.
How's that sound?
That sounds wonderful.
I have your approval, Jimmy.
Yeah.
All right. Cool.
Signing out in 3, 2.
Yeah. I expect my paycheck in the mail.